Okay, Euclid. Access intergate. Good. Now, search Euro code. And connect. And go France. All right.
Is Euclid speaking French now?
Hi, Kanwal. Sort
Hi.
of. I've just connected him through the intergate system to a network in Paris. You know, I don't know why, but I've had this really strong interest in France lately.
Ah, you're probably just gearing up for our show today.
Our show today? What does France have to do with quadratic equations?
You know, there's a strong connection between quadratic equations and France.
Really? Tell me. No, don't tell me. Let me guess. Okay, I'm already hooked up to the French network, so I bet you that I'll be able to find the connection between quadratics and France before the end of today's show.
All right.
And if I win, I get your coffee mug.
Oh, no, those stakes are too high. I couldn't give you my mug.
Oh. Okay, what about your sweater then?
What about my sweater?
Where do you shop anyway, Kanwal?
Oh, at a little boutique called Square Root. Do you like it?
It's, very mathy. Anyway, it'll be mine by the end of the show, okay?
Hey, wait a minute.
Hello. You're watching Math Shop, where we translate the international language of mathematics into everyday life. I'm Christine, and this is my partner and math coach, Magnifique Kanwal.
Bonjour.
And this multinational machine is my homemade computer, Euclid. In today's program, you'll learn what a quadratic equation is,
What the standard form of a quadratic is.
how to solve quadratics in the standard form using factoring and the quadratic formula,
What the discriminant is, and how to use it to predict the type of solution you'll get.
and we'll do a little piece on imaginary numbers. Okay, Euclid and I have some research to do.
But what if you need Euclid for the show?
Don't worry, we'll share them. Besides, it's only going to take me a few minutes to find out what the connection is between quadratic equations and France.
If you say so. Let's begin at the beginning and ask, what is a quadratic equation? It's any equation that contains a squared variable, such as x squared. Now, these are all quadratic equations because they all have variables that are squared. Such equations are often referred to as polynomials of the second degree because one of the terms is raised to the second power. 7x squared, 3f squared, 9g squared. Now, the standard form of a quadratic equation is a x squared plus bx plus c equals 0. Now, to best solve a quadratic equation, you should always convert it to standard form. It makes it easy to factor and easier to apply something called the quadratic formula. But I'll tell you more about that later. Now we need Euclid. If it isn't too much trouble.
Oh, no problem. I've just been reading about the geometry of a croissant.
Fascinating, but that isn't the connection.
I knew that.
An interesting feature of any quadratic function is the type of graph it forms. Euclid graph mode. This curve is called a parabola. The reason the quadratic function forms such a graph is the x squared term. If I look at a simple quadratic, like y equals x squared, and chart some values for it, I get these results. As the positive values of x decrease, so does the value of y. 3 squared is positive 9, 2 squared is positive 4, 1 squared is 1, and 0 squared is 0. But when I square a negative number, I get a positive result. A negative times negative always gives a positive. So instead of the graph continuing downward, as x gets more negative, it starts going upward again, forming a mirror image. Negative 1 squared is positive 1, negative 2 squared is positive 4, and so on. As I mentioned earlier, this shape is called the parabola, and it is characteristic of all quadratic functions. Its position on the graph and how gradual or how steep the curve is will change depending on the terms in the quadratic function. Let me quickly show you. In the shaded box, you can see the standard form of the quadratic equation. The example below it shows the simplest quadratic function, where b is 0 and c is 0. The x squared term on its own, with a coefficient of 1, creates the typical or standard parabola shape you see here. Changes in the terms of the quadratic equation will result in shifts and changes in the shape of the parabola. For example, if I change the c term, the parabola will shift either up or down. If it's negative, as in this case, it shifts down. If c is positive, as in this example, the parabola shifts up. There is a lot more we could tell you about graphing quadratics, but we deal with that in another episode of Math Shop. Today I'm going to focus on solving quadratic equations using the principles of algebra, which is a lot more precise than graphing.
Are you finished yet?
Yeah, for now.
Good, because I have a sneaking suspicion that this has got something to do with the Eiffel Tower.
To solve a quadratic equation with algebra, there are two different methods we can consider. One is factoring, and the other is the quadratic formula. Let's start with factoring. Whenever you have a quadratic equation, always check to see whether it can be factored first. Here is an example. 3x times x minus 4 equals 2 brackets x plus 1 plus 3. Before you can solve a quadratic equation, it must be in the standard form, which means that one side of the equation must be equal to 0. And sometimes it may not even look like a quadratic equation, as in this case. However, by expanding some of the terms, the square term will often show itself. Watch. I multiply, I have 3x squared minus 12x equals 2x plus 2 plus 3. Sure enough, when I expand the terms, I find there is an x squared term here, 3x squared. Now, let me do a little bit more work to get it into standard form. I have 3x squared minus 12x equals 2x. Let's collect the like terms, plus 5. Now, I'm going to subtract 2x plus 5 from both sides of the equation to give me 0 on one side. This is 3x squared minus 12x minus 2x minus 5 equals 0. Now let's simplify further. 3x squared, collect the like terms, minus 14x minus 5 equals 0. And now this last line is in standard form. Can you tell me why? It is in standard form because one side of the equation is equal to 0. And the terms are in descending order, x squared, x, and the units. Now I'll factor the left side of the equation. You can use any method of factoring you have learned earlier if it applies. I see that this is a trinomial that has a coefficient other than 1 for the x squared term. This means that I'll have to use the 7-step factoring method we introduced in an earlier program. Christine, I need Euclid again.
No. Are you trying to sabotage my research?
But you said we could share.
All right. I was just closing in on it, too. Do you have any idea how much math is in a cup of cafe au lait? Never mind. All right, Euclid, go factor mode. Step 1 is to multiply the first coefficient by the last number in the trinomial, which gives us negative 15. The second step is to list all of the possible factors of negative 15. Step 3 is to select the pair of factors which, when added together, will give negative 14. So that's 1 and negative 15. Now, in the fourth step, rewrite the trinomial using 4 terms instead of 3. In other words, replace negative 14x with 1x and negative 15x. In step 5, separate the first 2 terms and the last 2 terms, making 2 groups. In step 6, take the largest common factor out of each pair of terms. In this case, that is x in the first group and 5 in the second group. Now, in step 7, I see that 3x plus 1 is common to both. So I can rewrite the polynomial as 3x plus 1 times x minus 5. And there, the equation is factored. Now to make this equation true, the left side must be equal to 0. And for that to be true, the contents of either one set of brackets or the other must be equal to 0. So the two possible answers to this quadratic equation are negative 1/3 and positive 5. Hey, that's my research.
Yeah, sure.
Yeah, look, milliliters, liters, percentage. There's a lot of mathematical information here on this wine label. Mabel, that's it. My cousin Mabel. She's got the entire Encyclopedia Mathematica. If that doesn't show me what I'm looking for, nothing will. Okay, Kanwal.
Yeah?
I've got to go out for 5 minutes. You stay here, okay?
Okay. Actually, the French connection has to do with the historical evolution of algebra. For many centuries, mathematicians considered only equations with numerical coefficients. Letters were not used. This meant they had to repeat the whole process of calculation for each possibility. Using letters for coefficients instead of numbers in an equation yielded more general and helpful information. On top of that, mathematicians did not recognize negative numbers. For example, if we have an equation like this, x plus 5 equals 3, we can rewrite it as x equals negative 2. But before the acceptance of negative numbers, this would have been impossible. Therefore, a totally different type of calculation was needed for each type of equation, which was very slow and cumbersome. Then about 1550, the French mathematician François Viet, yes, that's our connection, the French mathematician François Viet introduced the idea of using letters to represent the coefficients of an equation. The combination of the two ideas, negative numbers and letter coefficients, meant that all quadratic equations could be written in the form ax squared plus bx plus c equals 0. And it was then possible to develop a single formula that could be used to solve any quadratic equation. It's called the quadratic formula. It was derived by isolating the x on one side of the quadratic equation. Now I want to show you how to use this formula, and the best way to do that is to work through a couple of examples. Here's the first. And it's already in standard form. X squared minus 4x plus 2 equals 0. In this case, a equals 1, b equals negative 4, c equals 2. By substituting into the formula, I get x equals negative 4 plus or minus the square root of negative 4 squared minus 4 times 1 times 2 all over 2 times 1. Now you have to be careful here. Watch for the positive and negative signs closely. And now Euclid will solve the rest for us. Euclid? Negative 4 is positive 4. Negative 4 squared is positive 16. 4 times 1 times 2 is 8. And 2 times 1 is 2. 16 minus 8 is 8. By factoring what's under the radical sign, I get the square root of 4 times the square root of 2. The square root of 4 is 2. Now dividing both the numerator and denominator by 2, I get 2 plus or minus the square root of 2. And this is as far as I can go. The two possible solutions are 2 plus root 2 and 2 minus root 2. Now let's do another example using the quadratic formula. But before we can apply the formula to this equation, we need to get it into standard form. To get rid of the fractions, I multiply both sides by the lowest common denominator, which is x squared. X squared and x squared. Now let's multiply. 3 x squared equals 5x plus 2. Now, to give the standard form, I subtract 5x plus 2 from both sides. This gives me 3x squared minus 5x minus 2 equals 0. And now that I have the standard form, I can substitute into the quadratic formula, which gives me x equals negative 5 plus or minus the square root of negative 5 squared minus 4 times 3 times negative 2 all over 2 times 3. Now, let's have Euclid take this the rest of the way. Euclid, take over. Negative 5 is positive 5. Negative 5 squared is positive 25. Negative 4 times 3 times negative 2 is positive 24. And 2 times 3 is 6. 25 plus 24 is 49. And the square root of 49 is 7. So, the two possible solutions are 2 and negative 1/3. Did you find the connection?
Not yet, but you can kiss your sweater goodbye. It's only a matter of time. I bet you it's something historical, like, you know, the French Academy inventing the meter or Napoleon's theorem or something.
Okay, I'll just keep going. There is not much time left, you know.
I know, I'm looking.
Okay. Once you know the quadratic formula, it can help you predict the types of answers you'll get for a quadratic equation. You can do this using something called the discriminant. The discriminant is the part of the quadratic formula under the radical symbol. In other words, b squared minus 4ac. By substituting values from a quadratic equation into the discriminant, I can predict the type of results I'll get. Christine can show you more clearly on Euclid. Can you help us out with this?
Sure. I've got nothing better to do. Euclid, if the discriminant is equal to 0, the result is always negative b divided by 2a. Then there will be only one real number solution to the quadratic equation. If the discriminant is positive, then there will be two real number solutions. The answers are indicated by the 2 points of intersection of the x-axis and the parabola. If the discriminant is negative, there are no real number solutions. In this case, use the quadratic formula to solve the equation.
I'll take over now, thanks.
You're welcome.
Now let's do some examples. X squared minus 6x plus 9 equals 0. If I substitute into the discriminant, I get negative 6 squared minus 4 times 1 times 9, which is 36 minus 36, or 0. In this case, the discriminant turns out to be 0. So there should be one solution to the quadratic. Euclid, complete the calculation for us. If the discriminant is 0, then all we have left to calculate is negative b divided by 2 times a. And that gives us negative 6 divided by 2 times 1. So x equals positive 3. Okay, another example. 2x squared plus 3x minus 1 equals 0. Let's find the discriminant. 3 squared minus 4 times 2 times negative 1, which is 9 plus 8, or 17. In this case, the discriminant is 17. Because the discriminant is positive, the solution should have two real number solutions. Now, 17 is not a perfect square and not easily factored. So we'll use the quadratic formula. Euclid? My equation is 2x squared plus 3x minus 1 equals 0. I substitute into the quadratic formula and then perform the algebra. Now I have negative 3 plus or minus root 17 divided by 4. If I complete the calculation, there are two solutions, both real numbers, just as the discriminant predicted. Let's do one more example using the discriminant. X squared minus 2x plus 4 equals 0. Let's find the discriminant. Negative 2 squared minus 4 times 1 times 4, which is 4, minus 16, which equals negative 12. In this case, the discriminant is a negative number. So the solutions of the equation will be two non-real numbers or complex numbers. But before Euclid completes the calculation using the quadratic formula, let me explain how to handle the square root of a negative number. Watch what happens when I try to find the square root of negative 12 using my calculator. 12 negative square root. I get an error. The square root is the opposite of squaring a number. And whenever we square a number, whether it is positive or negative, we always get a positive result. Therefore, the root of a negative number does not fit within the real number set.
To handle the root of a negative number, mathematicians have another system of numbers called the complex numbers. Complex numbers are a combination of all the real numbers and other numbers we call imaginary. But don't let the term imaginary fool you. They aren't that imaginary. And in fact, they're used a lot in engineering and physics. But how, you might ask, are we supposed to work with these numbers?
Because imaginary numbers cannot be expressed using our number system, they are represented by lowercase letter I. I is equal to the square root of negative 1. Let me show you how to use it in an example. In this example, we have the square root of negative 4. The answer is not 2 because 2 times 2 is positive 4. The answer is not negative 2 because negative 2 times negative 2 is also positive 4. The solution to this radical is an imaginary number. Watch. First, we factor. The square root of negative 4 is also equal to the square root of positive 4 times negative 1. Then we separate the radical into 2, giving us the square root of 4 times the square root of negative 1. The square root of 4 is equal to 2 times the square root of negative 1. Now, the square root of negative 1 equals I. So, my answer is 2I, an imaginary number. Whenever you have the root of a negative number, factor it to generate an expression that has the square root of negative 1. Simply substitute the letter I for the square root of negative 1 to express your result. Now let's go back to the problem we were doing earlier where the discriminant was negative 12. Here's our original quadratic equation. X squared minus 2x plus 4 equals 0. I substitute into the quadratic formula. Notice the negative 12 under the radical. I factor the root of negative 12 and then factor the root of negative 3. Coming at last to the square root of negative 1, the imaginary number. I substitute the letter I for that. So, the two complex number solutions are 1 plus the root of 3 times I, or 1 minus the root of 3 times I. And now we're nearly done. We just have time to summarize what we've covered today. Christine?
It's not fair. I'm so close. I just know it. Can't we run a longer program today? All right. But that sweater and your mug will be mine one day. You'll see. Okay, here's a summary of today's program. Euclid? A quadratic equation is any equation that has as its highest term a squared variable. Quadratic equations can best be solved by converting them into the standard form. ax squared plus bx plus c equals 0. Once the equation is in this form, you can then apply one of two methods to solve it. One is to factor the equation using any of the factoring methods for trinomials that we learned in earlier episodes. Or you can use the quadratic formula. The quadratic equation provides the discriminant b squared minus 4ac, which can be used to predict the kind of solution an equation will yield. If the discriminant is 0, then only one real number will be your solution. If the discriminant is positive, you'll get 2 real numbers as your solution. And lastly, if the discriminant is negative, you'll get 2 complex numbers for your solutions.
Remember that the quadratic formula will always work for any quadratic equation. But don't throw out factoring, because it may be faster in some cases.
Well, we really are out of time now. I can't believe I didn't get the connection between quadratic equations and France.
What, you give up?
I guess so.
Well, I'll give you a hint.
Really?
Yeah. Watch this show. Goodbye.
Watch this show? What do you mean? Goodbye. Tune in next time to Math Shop. What do you mean, watch this show?
I mean, the answer is on the tape.
The answer's on the tape? You told everybody the answer while I was out getting those encyclopedias?
Yeah.
Very nice if you can, Well. No, I'm fine. Really. It's humiliated me in public. It's okay. No. Really, an apology isn't necessary. I'm crying here.